Babies, how we doing? So, welcome to our last video lesson on static electricity. Today we're going to talk about the concept of what's called an electric field. So, electric field is kind of putting it all together. So, we talked about the idea of charge and how things accumulate charge, and that charge is just simply, whether it's the balance or imbalance of electrons, and the transfer of electrons between two objects. We then focus on the force that acts between them, what's called Coulomb's law, which recognizes that magnitude of that attraction or repulsion between two charges. But really what this idea of an electric field comes from is how do we have two things, charges in this case, that can affect each other, can apply a push or a pull when there's no contact being made. So this is the concept of what's called a field. In a field, you can think of it as a region of space, like looking at an outdoor field. And this first was developed by a guy by the name of Michael Faraday. And his idea was trying to focus on the relationship between electricity and magnetism. He recognized, and this is something we haven't talked about, that when you send electricity through a wire, say that we sent electricity this way through a wire, that if you were to place a compass near that wire that had a needle pointing north and south, that needle would point in a certain direction. This might not be correct, but you would have a current moving through a wire that would then affect the compass that normally reads a magnetic pole. So he was realizing that there's something about this wire that is affecting something else. So somehow the wire is affecting the space around it such that when you bring another object near it, it's also going to be affected. And that's the idea of a concept of a field. You can have a gravitational field. In this case, we're going to focus on an electric field. You can have a magnetic field and so on and so on. But the idea is that a field is going to be the region of space surrounding an object that has some property. So if it's gravity, it's mass. If it's an electric field, it's going to be charges. And that the region of space around that charge is going to create that force of attraction. For example, if it's gravity, attraction or repulsion for electric fields, and same thing with magnets. Okay, so it's key thing is that it's a region of space. So what we're going to look at is how do different charges affect other charges, how they affect the region of space around them, I should say, that then affects other charges. So what we're going to do first is we're going to talk about how do we find the magnitude of an electric field, and then we're actually going to look at how do we represent this region of space. How do we represent a field if it's something, again, that affects other objects? Key thing here is, again, this is something we do not actually see, so it's by definitions that we've come up with the different ways that it looks to help explain the things that we do see. So to kind of go through this, what we're going to look at is kind of define two things. We're going to find what's first called a source charge. So the source charge is going to be one of the two charges. Again, think of Coulomb's law, that Q1 and Q2. The source charge is going to be the charge that actually creates the field. And then we are going to have the test charge, and the test charge is going to be the object that experiences the push or pull. So think of this as like gravity that we experience every day. Gravity is created by the Earth, and then we are the ones that are experiencing that field. So we would be the test mass, where gravity would be the source mass. All right, so to find the electric field strength, by definition, the field strength is going to be the amount of force a charge experiences based upon the amount of charge that it has. Okay, so that's why we have the equation F over Q. F represents the amount of force, and little q here is going to represent the test charge. So it is the force per unit charge that something would experience. So for example, if it experienced, I'll write it up here, about 5,000 newtons of force, and that the charge was, let's say, 5 times 10 to the negative 6 coulombs, then we could represent the strength of that field. And unit-wise, you're going to see that it's newtons per coulomb. Okay? So to kind of simplify this, we already know, we just went through that the force experienced between two charges is equal to K, Q1, Q2 over D squared. That's Coulomb's law. So if I were to take that equation and divide it again by little q. So understand it in this equation, I'm going to do this. I'm going to replace, instead of Q1 and Q2, here's what I'm going to do. I'm going to write little q and big Q. So think of little q as the one that is experiencing the charge, the field, that's the test charge, and capital Q as the source charge, just to show the difference between the two. So when I use these two equations, this one equation involving the other, Coulomb's law, into the electric field, it gives us a way that we can actually find the magnitude of that field. So if I just look here and both of these test charges are in the equation, so numerator and denominator will cancel out, what ends up happening is I get this. I get K, which is that Coulomb's constant, times capital Q, which would be the source charge, divided by the distance squared. And this is the equation that's going to allow us to find the magnitude of the electric field. Okay, so magnitude of the electric field. Magnitude, again, represents the strength. So it's dependent upon that Coulomb's constant. It's dependent upon the source charge, and then you see that distance squared again. So this equation is another one of those inverse square laws. And again, what this means is that as you get further away, the field's going to get weaker. As you get closer to it, the field would get stronger. So again, what this relationship is going to do is it's going to allow us to find the magnitude of the electric field created by a source charge. So in this equation, again, capital Q is going to represent the source charge, and then D is going to represent the distance away from that source charge, and then that K value again is going to just represent that Coulomb's constant. So this is going to find the strength of the field. Okay, so if I were to look at this first one, say we have a 43 nanocoulomb charge, and I want to know what is the strength of the field at a distance of 0.30 meters away. So notice that this is very similar to the type of questions I was asking with Coulomb's law. The only difference here is that we only are given one charge, which is the source charge. So I'm just going to simply plug in my variables again. So my electric field would equal, my K value again is 9 times 10 to the 9th. That's at 9 billion. The test charge is 43 nanocoulombs, which would be 10 to the negative 9th. It's for nano. And then divide that by the distance, which would be 0.30, so 30 centimeters away. And I'm going to square that distance. By plugging that in, I'm going to get an electric field equal to 4,300. And then unit-wise, it's going to be newtons per coulomb. Okay, so newtons per coulomb, which is kind of a different unit, but what that newtons per coulomb represents is that it describes how much force a charge would experience. So if I had, for example, 1 coulomb of charge, so if I had 1 coulomb, it would experience 4,300 newtons of force. If I had, for example, a half a coulomb, it would experience 2,150 newtons of force. Okay, so it describes how much force a certain amount of charge will experience. Specifically, since it's per coulomb, it represents 1, but by looking at how many coulombs I have, I can then analyze the force. All right, next thing we're going to do is look at what happens when we make some changes. So we're going to look at first what happens when I cut the distance in half. Okay, so it goes from 0.30 meters, so 30 centimeters, down to 15. So if I were to calculate my electric field strength at that point by using 9 times 10 to the 9th again, my same charge of 43 nanocoulombs, so 10 to the negative 9th, but now instead of 0.30, I'm going to use 0.15 meters, and I can square that. So again, the difference here is we're cutting the distance in half. So what that would do is turn my electric field up to 17,200 newtons per coulomb. Okay, so now I should see that my electric field is going to increase, and it's increasing by a pretty large amount. All right, so if we want to compare these two again, kind of like we did with Coulomb's law, just to kind of look at the difference in how it changes if I were to take, if I were to take 17,200 newtons per coulomb and compare that to the original value, 4,300 newtons per coulomb, what I should see is that it is 4 times bigger. Okay, so by cutting the distance in half, what we're seeing is that the electric field, God bless it, is going to be 4 times bigger. And again, that is that inverse square law. By cutting it in half, electric field is going to get stronger. Okay, now the inverse means opposite, so opposite of half is double, but because it's an inverse square, that double becomes squared, which would be 4 times bigger. All right, next one we're going to do is look at what happens when I make the distance bigger. So now the distance is going to be 0.60 meters. I did it again. All right, so we're going to take that same equation. I'm just going to be lazy. We're going to use the same variables, KQ over D squared. The only difference now is that for my distance, I am plugging in 0.60 squared. Everything else is going to stay the same as before. So that would give me then my electric field would equal 1,075 newtons per coulomb. So again, if we were to compare that to the original value that we had before, And that original value, again, was 4,300 newtons per coulomb. Compare that to the 1,075 newtons per coulomb, and that would mean we're going to get a factor of 4 again. However, we see the value got smaller, so what we're seeing is that it's 4 times smaller, which is the same thing as that we cut our electric field into fourths. Okay, so again, inverse square law, when I doubled the distance, opposite of a double is a half, but because it's squared, we see that it's a cut into a quarter. Okay, so we're seeing the same sort of relationship we saw with the Coulomb's law equation that we're seeing with the electric field strength. All right, last one here we're going to look at is what were to happen if we were to double the source charge. So we're going to make the source charge bigger. So the source charge was 43 nanocoulombs, so if I were to double that, I should get 86 nanocoulombs. I'm still going to stay nano. So I'm going to use my same relationship here, KQ over D squared. Okay, but what we're going to do now is we're going to change the source charge from 43 nanocoulombs to 86 times 10 to the negative 9th coulombs. Okay, and with our distance, just so we're aware, we're going to go back to the original one. Again, we're going to compare it to the original. So for our distance, let's just make sure that we are using the 0.30 meters squared. Okay, so if I were to plug that in, I will get an electric field strength equal to 8,600 newtons per coulomb. So again, to compare 8,600 newtons per coulomb to our original value of 4,300 newtons per coulomb, we're going to get a factor of 2, which means that it's 2 times bigger than what we saw before. So again, by doubling the source charge, we're seeing that it's doubling the electric field strength. So it's the same kind of relationships that we saw with the Coulomb's law equation, and that is because technically the electric field strength equation comes from that Coulomb's law equation. So again, this is looking at the magnitude of the electric field. We have one more video lesson we'll do with this unit that's going to look at how we actually visualize this electric field. But again, an electric field is going to describe how a source charge affects the space around it, which is going then to relate back to the force of attraction or repulsion that another test charge would experience. If you guys got any questions, make sure you jot this down. Otherwise, go ahead and watch that next video lesson on the electric field directions and what it looks like.